under these kind of heat stress conditions to drive you to the point of overexertion. And when you get to that point, you have to do one of two things. You either have to quit what you're doing or suffer the adverse consequences, which very often are a heart attack. We mentioned this term, uncompensable heat stress environment. This is not unique to firefighters, but firefighters kind of carry it to extremes. That's kind of one of the things about you guys. You don't do things half-assed, okay? A football uniform is an uncompensable heat stress environment, okay? But it's nothing compared to your bunker gear, okay? But they do the same things. They impair your body's ability to lose heat. And the compensation mechanisms that we have, the sweating and that kind of stuff that we do to try and compensate and get rid of the excess heat, don't work very well. In fact, your bunker gear has the ability to basically stop heat transfer from the body completely. Okay? Now, things like a football uniform will reduce it like 75 or 80%. But your turnout gear that you wear into a fire can stop it completely. As you look at the construction of this, this is the basic 1971 NFPA definition of your gear, what it's supposed to, the primary components of it. Has to have an outer shell that's abrasion resistant and also flame resistant. In other words, direct flame impingement for a short period of time doesn't cause it to catch on fire. Inside there's a moisture barrier. What's that moisture barrier for? If you get hit with the hose line, its job is to keep that water outside. Because we know we don't want any excess water inside our turnout gear. Number one, it gets very heavy. And number two, when you get a lot of water inside your turnout gear and it gets really hot inside that turnout gear, what happens? Steam burns. Okay. Then the inner layer is your primary thermal barriers. That's that quilted layer that's inside your gear. It's quilted primarily to generate some airspace between the material and you, but there's still a lot of contact. Okay. That airspace is there because that airspace is a great insulator. Air is a tremendous insulator, heat insulator. So having that airspace in there is very good. And when you get somebody who's stupid enough to put their hand on you and push all that stuff together and remove that airspace and put that stuff right against your skin with a tool or something, you get a conductive heat burn, okay? And so that's what this is all designed for. It's all designed to reduce heat transfer and water movement from here to there. But there's a consequence to that. Okay? So here's your bunker gear. Here's the fire. Lots of heat. Now we said that this bunker gear is not a perfect insulator. And so some heat from out here does leak in. The majority of the heat that's inside that bunker gear is the metabolic heat. Okay? What are the consequences of this condition? We've already talked about a bunch of this. Rapid increase in temperature inside the gear. Okay? That causes an increase in core temperature. Increase in sweat rate. Within about 2 or 3 minutes of being fully encapsulated, your sweat rate is maximized. Just to give you some numbers here, at maximal sweat rate, 180 pounds, 6 foot tall, 180, 190 pounds, 6 foot tall, physically fit firefighter can lose close to 1 liter of water an hour just through sweat. Okay, that's a lot of water. Okay, most people can't do that. One of the real bad problems about though is after the fact. We only have the ability, that same person who can lose 1 liter of water an hour can only replace about 60% of that an hour. So about 600 milliliters an hour. A bigger person, more muscle mass, more body surface area, can lose you know, I don't know, 1,200, 1,300, maybe even 1.5 liters of water an hour. Well, how much body water do you have in your system? Well, not enough to spare 1.5 liters for very long. Okay? So we get the pouring out of sweat in an attempt to cool yourself, but we know that that doesn't work. You get rapid dehydration. So your body is trying to compensate, and it's just dumping sweat out, but it's not cooling, and it gets into this vicious cycle where it sweats and it sweats and it sweats, but the body temperature is not going down. The core temperature is not being, continues to rise. And cranking up the sweat rate till it's maximized. You're sweating out water as fast as you possibly can, but it's not cooling you. And as a consequence of all that sweating, you're very quickly losing body water. You're dehydrating. That, if you go back to those beginning definitions, that's what dehydration is the loss of that body water through whatever means. Okay? We'll talk about how we lose body water and how we gain water and all that kind of thing in a minute. But that's the point. It's a very rapid dehydration. It doesn't matter how physically fit you are. It doesn't make any difference how tough you are. It doesn't make any difference how acclimatized you are. When you get in that situation, you're dumping sweat, you're dumping body water as fast as your body can possibly do it, and you're dehydrating very quickly. Okay? If you started from a poorly hydrated system to start with, you're in real trouble. How many of you think you're hydrated right now? Let me show of hands. How many think you are? How many of you think you're properly hydrated? Okay. Why do you think you're properly hydrated? Do you monitor your hydration?
I mean, for the most part, I kind of track like how much I drink during the day,
Mm-hmm.
like how much electrolytes I'm taking in. You know, I monitor when I pee, like how the color of my urine.
Mm-hmm.
That's how I've been taught, like, to judge where you're at hydration-wise.
Right. And those are all good mechanisms, and we'll talk about all those ways to monitor your hydration. And those are all good things. You can look at your body weight, the color of your urine, lots of things. But there are problems associated with each of those monitoring systems, and we'll talk about those. Okay? I would guarantee you that of the 12 of you, I would bet some money that at least half of you are not properly hydrated right now. And that's not good. Because even though it's probably, 65 degrees and rainy outside, if you go out there and they light the fire in that burn building over there and you don that gear, it doesn't make any difference what it is outside. When you go in that building, guess what? You're right here. And this is happening. So if you go in there in a dehydrated state, you're asking for trouble. And this is the way most people, I would think, I don't know, I've never been through the school, I would think that this is probably one of the primary reasons people don't make it through this school. Okay. Let's move on a little bit here. Let's talk about water in specific. Total body water, so the total amount of water you have in your system. We put water in lots of different places in our body. Muscle tissue holds a lot of water. Fat tissue, not so much. Cardiovascular system has a lot of water in it. So there's a lot of ways to divide this up. But when it comes to hydration status and its effect on work performance, we want to divide it into different components. Extracellular water and intracellular water, or cellular water. Okay? The extracellular water is the water in the blood or the plasma. Okay? That's not inside cells, that's outside the cells. Interstitial water is the water that is surrounding the cellular tissue. It's not in the cardiovascular system, it's not in the blood vessels. It's outside of that, but it's surrounding the cellular tissue. It's not inside the cells. Why is that so important? Why is that interstitial water so important for for you when you're doing muscular work.
The only water we have readily available to ourselves.
Pardon?
It's the only water we have readily available to ourselves.
That's exactly right. The interplay between the intracellular water, the water that's inside those cells, and this water that is in the interstitial space outside the cell wall is where muscle contraction is generated. And you know that if you get dehydrated, one of the consequences of that can be cramping. Okay? And cramping is what we call a non-physiologic contraction. In other words, your brain and your nervous system is not initiating a contraction, something else is. And it's usually an imbalance of fluid between that, what's going on inside the cell and what's going on just outside the cell. That balance. Okay? So that's why I think it's important to divide it up in this manner. The other reason is that the plasma, the water portion in the plasma, or water portion of the blood, is this circulating fluid, okay, and carries out a lot of function of the cardiovascular system, carrying heat around, carrying nutrition around, getting rid of waste materials, supporting blood pressure, all those kind of things. And then there's the gut. A lot of water in your gut, okay? And we bring that up because when we start talking about the process of rehydrating or putting water back into this system, we dump it into our gut first, and then we have to absorb it from there into our system. It goes from there into the cardiovascular system, from the cardiovascular system into the interstitial space, and eventually into the cells, eventually back out of the cells into the interstitial space, to the sweat glands, and out of the body. So where does sweat come from? Sweat ultimately comes from right here. Okay? This is kind of the end point or the starting point for water in your body. This is where it's functional from a biochemical standpoint. And then it moves back through the system to the interstitial space, to the cardiovascular system, eventually out through or feces or through urine. And the ways we lose water. Dividing this in this way, and I say this because we can talk about body compartments like muscle versus fat and those kind of things. That really doesn't tell us much about why hydration is important to us from a work standpoint. So I want you to understand these things about where the water is, what role it plays in these places, and why it's important to you. The other thing is what we call third spacing. Third spacing is like synovial fluid in your joints and things like that. We're not too worried about that here. Okay? Those are more chronic issues with water, and we don't worry about it too much here. Although, if you're a medic, you know that water can hide there in some medical conditions. So, and then there's the water inside the cell. So extracellular versus cellular water, and we divide the extracellular water into these areas for a functional purpose. What does the water in the body do? Well, it's a circulatory fluid. We talked about it working as a radiator, carries heat away from the core or toward the core in cold environments, but we're not talking about those here. Carries cellular and extracellular waste material. So the cells produce things like carbon dioxide, it produces protein turnover and stuff, and excretes this stuff or diffuses this stuff out into the cellular or to the extracellular space, and the blood carries it away. Water carries it away. It's a solvent. Dissolves nutrients and electrolytes. Okay, we can't get electrolytes into our body unless they're dissolved in a fluid, water primarily. Okay, it acts as a lubricant in the joints and connective tissue, also in your gut, keeps things moving along. Get good and dehydrated. If you're good and dehydrated by about Thursday or Friday, you're not going to spend a whole lot of time on a crapper. Or if you are, it's not going to be very productive. Okay? Don't get in that position. All right? cushioning around organs and things like that, and then of course the excretion process. These are the primary roles of water, but we're primarily concerned in this class about its role in supporting cardiovascular function, supporting blood pressure, and dealing with heat stress.